Substitution reactions. What are they and what do they look like? Well, without knowing what they are, let's first analyze what we have here. This bromine atom, it's going to be a leaving group because it has a high electronegativity, so it wants to take electrons and just leave. How about that compound on top of the arrow? Well, we can rewrite it for what we know it to be because that Na plus is just a spectator ion. So Na plus, that means that the Cn gets a negative charge. Let's rewrite that Lewis structure below the arrow. That Na plus, we don't care about it, right? It's a spectator ion and it doesn't really matter to the reaction mechanism. What we care about is the Cn, the C triple bonded to an N that has a negative charge and a lone pair. This has high electron density, so it's a nucleophile. Nucleophiles want to react with carbons, carbocations, and share their electrons. What does this reaction look like? Let's write that mechanism down here. So we have that original compound, the alkyl halide, with the bromine at the end, and the nucleophile, the cyanide. So first thing, the bromine takes those electrons and leaves. Simultaneously, the nucleophile reacts with the carbon and replaces the bromine. So just the original alkyl halide, except for instead of the bromine, we now have a cyanide at the end. What are the characteristics of this type of reaction? Well, it occurs in one step, right, as is evident by the mechanism that we just drew, and so it's pretty fast. It's also bimolecular, meaning that the rate relies on the concentrations of both the substrate and the nucleophile. So rate equals rate constant times the concentration of the substrate times the concentration of the nucleophile. What do we call this reaction? Well, we can call it SN2. But why SN2? Well, the S just stands for substitution. That's the sort of reaction that's happening here. We're substituting the bromine for the cyanide. The N stands for nucleophile because cyanide is the nucleophile that is doing the substituting. And the 2 just stands for bimolecular. So bimolecular means that the rate of the reaction depends on the concentration of 2 species. In this case, the concentration of the substrate and the concentration of the nucleophile. Well, how about this reaction? I mean, you probably can guess it's another substitution because that's a leaving group. And it follows from that water is probably a nucleophile. And indeed it is a nucleophile. It's not the best nucleophile because it does have a negative charge, but it does have lone pairs. So it is a nucleophile, and in this case it'll act as a nucleophile. What does this reaction look like? This is a little different, as you can see, because that bromine is bonded to a carbon that's bonded to 3 methyl groups. So it's a tertiary carbon. And so this reaction mechanism is going to be different. It's going to go in steps. The first step is that bromine just leaves. No nucleophilic attack, the bromine just leaves. And what does it leave? A carbocation in its place, because that middle carbon is only bonded to 3 things now. How about that second step? Well, we have our carbocation that we formed in step 1, and now the nucleophile, the water, is going to come in and attack it. Has its lone pairs, it's going to attack that, and it's going to form this complex. So we form this sort of tert-butyl water complex here. And this oxygen is bonded to 3 things, so it has a positive charge. But we're not done yet. Even though we did technically substitute the leaving group, another water molecule reacts with the compound that we just formed. And now what it does is it abstracts a proton from the water on the molecule using this reaction mechanism. And it forms this tert-butyl complex that is bonded to an OH. So our end result is a Br substituted for an OH. This reaction is pretty unique because the water here is acting as both the nucleophile in step 2 and the solvent in step 3. Then this is the nucleophile here, the one that bonded to the tert-butyl in step 2, and then the solvent reacting with the nucleophile. And this general sort of reaction is called a solvolysis reaction, but what you need to know is that it just follows an SN1 mechanism. SN1 reactions can follow either the solvolysis mechanism or just a general nucleophilic substitution mechanism for SN1. And admittedly, the SN1 mechanism is pretty complicated, but I think we can simplify it to a way that's both simple but still thorough. So for SN1, we have our leaving group bonded to the tertiary carbocation, and the first thing that happens is that the leaving group leaves without nucleophilic attack and forms a carbocation. Then the nucleophile comes in, performs nucleophilic attack, reacts with the carbocation to form the original compound, but with a nucleophile instead. And this reaction is pretty slow because the first step is the slowest step and is thus rate determining. And as such, SN1 is unimolecular, right? So the rate, if we were to write it out, is equal to the rate constant times the concentration of just the substrate. SN2, it's how we discussed before. There's a leaving group bonded to a primary carbon, and the nucleophile both reacts and the leaving group leaves simultaneously. So we're going to have this transition state where it looks like the middle carbon is bonded to 5 things, right? four things and then the nucleophile, but we draw out the bonds of the nucleophile and the leaving group as dashed lines because they're both forming and breaking at the same time. And what do we get as our product? The original compound, but with the nucleophile instead at the end. And so, as we discussed before, this reaction is fast, and as such, it is also bimolecular. So the rate is proportional to both the concentration of the substrate and the nucleophile. And although this looks like two steps that I wrote out, and this is just the transition state in the middle. It's just an activated complex with high energy. So in reality, SN2 is just one step. And I think this is probably the best study tool that's ever been invented. I mean, stuff like this is pretty rare. The nucleophile being the orange cat and the leaving group being the gray cat. In the first column, the gray cat gets up and leaves, and then the orange cat comes and takes its place. In the second column, it kind of looks like the orange cat is pushing out the gray cat. So in that middle, the orange cat is getting into the spot while the gray cat is being pushed out at the same time. And that's pretty close to the mechanisms of SN1 and SN2. So I think this is awesome, and this is a very great way to remember how the reactions work. Yeah, that's substitutions.